we have seen how the CFD method works in principle for the case of finding out the laminar flow, steady flow through steady fully developed flow through a duct of rectangular cross section. We have seen the method. Let us now try to work it out and get to know better how the CFD solution works. So we are going to take again the case of a rectangular cross section, and we solve the corresponding Poisson equation for it with actual numbers to see how the solution evolves using the CFD approach. So what we are looking at is steady fully developed laminar flow through a straight duct of rectangular cross section. So we take the geometry to be like this. The equation that we are interested in is dou square W by dou x square plus dou square W by dou y square equal to dP by dz times 1 by mu. When we want to work out, we have to put some numbers to this. So we will put this whole thing to be equal to 1. So this is the equation that we want to solve, subject to this domain, and we will put some numbers to this very soon, and subject to the condition that W is equal to 0 on all walls. So the first step of the CFD solution is that we have a governing equation, and we have the boundary condition, and we have a flow domain with the actual dimensions of this flow domain yet to be specified, and we should put here this as being equal to -1, because mu here is the dynamic viscosity, which is constant, and pressure gradient is negative in the positive flow direction. So if you want W to be positive, then we should put a negative sign. So we will just put, for the nominal case of this value on the right hand side being -1. The second step of the CFD solution is to discretize the flow domain and identify the points, the grid points at which we want to evaluate the solution. This is a hand calculation. So in order to make this possible, we will take a small number of grids. We will divide this into 4 parts, 4 equal parts, and this into 3 equal parts, just to show the unequal thing. And we say that these are the intersection of these is where we want to measure, we want to find out the velocities. As per the boundary condition that W is equal to 0 on all walls, these are the wall points. This is where the velocity is 0. So in this we would like to know the velocities at these 6 interior points, subject to the condition that W is equal to 0 on all the other points, at all the other grid points, and that the resulting W distribution within this at these grid points satisfies this relation approximately. So we have to put some number here. So we will put I here in the x equal to constant planes to be 0, 1, 2, 3, 4, and j equal to 0, 1, 2, 3. So in this problem, the unknowns can now be listed. These are the value of W at this point, at these 6 points, and we can identify them with the I index and the j index. So these are Wi comma j, and since both I and j are in single digits, we can write this as Wij, and specifically we are interested in this point, which becomes W11, this is W21, this is W31, this is W12, this is W22, and this is W32. So there are 6 unknowns, and these are the values that we want to find, subject to the W distribution satisfying this condition and also this equation, where the right hand side is given as -1. So the pressure gradient divided by viscosity for this fully developed flow within this rectangular duct is this. Now here we are taking the case of delta x being constant, and let us put this as 1 unit. At this stage we do not have to specify what that unit is, it may be meters or millimeters and so on, and it depends on the actual problem. For the sake of the numerical example, we will take delta x to be 1 and delta y to be 1. We will do later on an assignment where these numbers are different. So under these conditions, now everything is specified here for us to launch our third part of the CFD problem. So we have taken the equations and we have discretized the points, and we have located the unknowns here, and so the next point, so this is step 1, step 2, and third step is to write down the approximate form of these equations, this equation, which is going to be valid at each point, and as we have said, we will approximate dou square W by dou x square at the location I comma j as Wi plus 1j minus 2 Wij plus Wi minus 1j divided by delta x square, and dou square W by dou y square at I comma j is approximated as Wij plus 1 minus 2 Wij plus Wi j minus 1 by delta y square. So this equation is going to be discretized using these approximations as this plus this is equal to -1 at a point ij. So we have finally the discretized equation. Is we can also take note of the fact that delta x is equal to 1 and delta y is equal to 1. So we can take note of this. So the denominator is equal to 1 here and it is also equal to 1 here. So we can directly substitute this as the discretized equation at point I comma j is given by this plus this equal to -1. I comma j plus W I minus 1j plus W I j plus 1 minus 2 Wij plus W I j minus 1 is equal to -1. So this formula we apply at each of the points at which we want to have the solution. So for example, we take this recurrence, this formula here, and we apply this at this point, this point, this point, at these points, and that will give us 6 equations that we get from this. So for this point we can say that point 1 comma 1 is this one, where it is 1 in this direction, 1 in this direction. So this means that I is equal to 1, j is equal to 1. So we substitute this here, we get W21 minus 2W11 plus W01, 1 I minus 1 is 0, plus W12 minus 2W11 plus W10 is equal to minus 1. Okay. So in this, these points with zeros are the boundary values. For example, W01 is this point, and W10 here, W10 is this point, and W01 is this point, and we know from the boundary condition that at all these points W is equal to 0. So where we know the boundary value here, we can substitute this. So this is equal to 0 and this is equal to 0, and we have minus 2W1 minus 4W11. So we can write this as minus 4W11 plus W21 plus W12 equal to minus 1, and we take this thing to the other side. So we can get W11 we take it here and then we divide by minus 4, so that will be 1 plus W21 plus W12 divided by 4. This is the formula for W11. We will do the same thing for the next point, which is this one. So that is 0.21. This implies that I is equal to 2 and j equal to 1. So we substitute these values again in this equation, and we should be getting W31 minus 2W21 plus W11 plus W22 minus 2W21 plus W23. This is 23 and this is 21, and this whole thing is equal to minus 1. Here there are no boundary points, so we can write this as minus 4 W21 is equal to, we can take all the other things onto the right hand side, minus W31 minus W11 minus W23. So this is 20, this is j is equal to 1, so this is 0 here, and 20 is this one, and this is 0 here. So there is a wall point. So this is like this, and so from this we can get W21 is equal to 1 plus W31 plus W11 plus W23 divided by 4. And we can do the same for point this point, that is 31 this implies I is equal to 3 and j is equal to 1. So let us see if we can do without any mistake. So W43 almost. So W41 minus 2W31 plus W21 plus W32 minus 2W31 and this is W30. So again W30 is the point at this value and W41 is this point, this is 0 and this value is 0. So this is 0 here and this is 0. If these values are different, we can substitute those values and then take them to the right hand side. So if the boundary condition is known, then that goes on to the right hand side, it will not appear on the left hand side as the equation. So we can rewrite this equation as minus 431 plus W21 plus W32 equal to minus 1. So this gives us W31 as 1 plus W21 so this is the equation for W31 and we can similarly do for point 1 2 here. This implies I is equal to 1 and j is equal to 2. So this is W22 minus 2W12 is W02 plus W13 minus 2W12 plus W11 is equal to minus 1. We are looking at this. So we have uh, 02 is 0 here and we should be getting 1 3 yeah. So we should be getting two wall values here. So this is 0 and this is 0. So 1 3 is 0 and 0 2 is 0. So both are wall values. So from this we get the expression for W12 1 plus W22 by 4. So this is the expression for W12. So we have to do these two expressions, and if we want we can look at a pattern that is developing. So the value at this particular thing is given as the right hand side here plus the neighboring points, this plus this plus this plus this, these two are 0, divided by 4, we can go through that. So for example 1 plus W21 plus W32 by 4, so we can do it like this, or we can do it the hard way. Let's continue the hard way. So this is 2 2, I is equal to 2 and j is equal to 2. Substitution of this expression into this, W32 minus 2W22 plus W12 plus W23 minus 2W22 plus W21 is equal to minus 1. So we are looking at this point here. So we have W23 is a wall value, so this is equal to 0. Okay, so we have, it will be 1 plus this plus this plus this divided by 4. So from this we can write W22 is equal to 1 plus W32 plus W12 and the last point is W.32. And here I is equal to 3 and j is equal to 2. So substituting this here, we get W42 minus 2W32 plus W22 plus W33 minus 2W32 plus W31 is equal to minus 1. And here we are considering this point, so this is an average of these 4, so there should be one boundary point here and one boundary point here, so that is 4 2 and 3 3. So this is 0 and 4 2 is 0. So we can write from here W32 is equal to 1 plus W22 plus W31 divided by 4. So by approximating at each of these discrete points at which we want to get the solution, by approximating the partial differential equation with finite difference formulas and coming up with a template here after substitution of delta x and delta y and the constants like this, we take this template and apply it to each point at which we want to get a solution, and from that template we will be able to derive the corresponding algebraic equations which give us the values, and we are expressing the value at W11 here in terms of these points, these expressions like this. So we find that there are 6 equations, A, B, C, D, E and F. These can be solved, these are algebraic equations, and these are such that we cannot solve any of these equations individually. So that is, we cannot from this equation find W11 and this equation, or from this equation W21 like that. So these are simultaneous algebraic equations, and these are also equations with constant coefficients. All of them have a coefficient of 1 or 0 or something depending on what we have here, and we can see that we have a set of linear equations with linear algebraic equations with constant coefficients which we get as a result of discretizing the governing partial differential equation at each point at which the value of the variable is to be evaluated. So we have converted, if you put all this into AW equal to B form, then the matrix A here will have the coefficients of all the variables, and we can write them down, and we can then invert the matrix. So that is one way of doing it, but in this example, typically in computational fluid dynamics, we do not directly invert the matrix for a solution of AW equal to B. It is because we normally deal with very large matrices. So inversion of those matrices is very expensive computationally. So we use some iterative methods, and we illustrate the application of the Gauss-Seidel iterative method. It is a fairly basic iterative method for the solution of A phi equal to B. At this stage, we take it as granted that this method will work for this set of equations. We will take a minute to explain how this iterative method works, and then we can actually look at the solution. So we consider a set of 3 equations involving 3 variables, a11 x1 plus a12 x2 plus a13 x3 is equal to b1, a21 x1 plus a22 x2 plus a33 x3 is equal to b2, and a31 x1 plus a32 x2 plus a33 x3 is equal to b3. So these are a system of 3 linear algebraic equations involving variables x1, x2, x3 with constant coefficients a11 to a33 given here, and also b11, b1, b2, b3 are given here, and we want to find out from this x1, x2, x3. There are many ways of doing this, and what we have in our example here is a set of 6 equations involving 6 variables, and we can write down all the 6 in the form of a 6 by 6 equation like this. And in the Gauss-Seidel method, we solve this iteratively by taking in the first equation, we express x1 in terms of x2 and x3, and we take this equation x2 in terms of x3 and x1, and then x3 in terms of x1 and x2 using the third equation, and we start with some guess value. We proceed with the iterative update of x1, x2, x3 from those given values until we reach a solution which is not changing further. So this iterative procedure is very easy to implement. It will work only under certain conditions. We will look at the conditions for convergence of this particular method. For the time being, we just describe here how the method works and how to implement it, and to get a solution from this. So from this we can write this as x1 equal to b1 minus a12 x2 minus a13 x3 divided by a11 x2 is b2 minus a21 x1 minus, this is a23 x3 divided by a22, and this is written as x3 equal to b3 minus A31x1 minus A32x2 divided by A33. Okay, so we have written these expressions like this, and we start with an initial guess. Which can, in the case of a convergent method, in cases where the Gauss-Seidel iterative method works, it does not matter what the initial guess is, the final iterative solution will work in all cases. So we can start with an initial guess 0 0 0 for x1 x2 x3, and we can get from this x1 x1 x2 x3 at the end of the first iteration by successively substituting in this, and then from this we get again x2 x3 in the second iteration by again substituting, and then we go on x1 x2 x3 for the kth iteration until we reach successive values of x1 x2 x3 which are not changing. Okay, so the way that we evaluate this is that xk plus 1 at the end of k iterations we have value of x1 x2 x3. So the new value of xk plus 1 is evaluated as xk plus 1 is b1 minus a12 x2 k and a13 x3 k, and x2 is evaluated as b2 minus a12 x1. We already have the k plus 1th value, so this is k plus 1 and this is k here, and x3 is evaluated as b3 minus a31 x1 k plus 1 and k plus 1 here. So in that way, given the kth values of x1 x2 x3, we can evaluate x1 k plus 1th value of x1 x2 x3 like this, and in this way we generate from a starting guess, we can generate successive values and we can get the solutions. So this is a method that we will use for the evaluation of this, and we can therefore write these equations in, already these are put in this Gauss-Seidel form. So we can say that W11 k plus 1 is W2 k, this here this is k plus 1 is 1 plus k, and we already have k plus 1, so we can put k plus 1 here, this is k. Here 31 k plus 1 is W21, we have k plus 1, W32 we do not yet have, so this has k. W2 k plus 1 is 1 plus W22 k, W1 k plus 1, W22 k plus 1 is 32 we do not yet have, so this is at kth value, this is at we already have this, so this is k plus 1 and this is also k plus 1, and finally the value of W32 is obtained as k plus 1 k plus 1. Okay, so we have here the formula for evaluating W11, W21, W31, W12, W22 and W32 from known values of the same variables at the previous iteration. So we start with the initial guess Wij equal to 0, and then we generate solution at the end of the first iteration, second iteration, third iteration like that, and then as we keep on going we will see how we can get how we will be getting a converged solution. So this iterative procedure is quite common and it is best illustrated when we tabulate the results. So we'll try to tabulate the results so as to get an understanding of how the solution evolves in this particular case with using this particular iterative method. In evaluating this point, we made a small mistake here. When j is equal to 1, so this is to I j plus 1, so this is W22 and this is 21 and this is 20. So this we put correctly, this we put correctly. Here we put it as 23, so that has to be corrected here and also here. So this is the formula. So now we'll try to do the solution of this using the Gauss-Seidel method in Excel, because that is very easy to see and we can also see how the solution evolves. So we'll take a look at this. We'll try to program the solution of these using the Gauss-Seidel method in Excel. So we'd like to get back. You want me to? Now, are they going to see that or?
Only this, only PowerPoint.
So just okay, we'll go into this. So here we have the formulas for the 6 points W11, 21, 31, 12, 22, 32, which are written as per what we have derived. For example, W11 is 1 plus W21 plus W12 divided by 4, like this. And here we are associating the 6 variables, and this is the solution at the initial guess. So we are giving this as 0 values for each of these, and the value here for W11 is coded as per this. 1 plus W21 is this one here, so that is B2, plus W12 is D2 divided by 4. And if you consider, for example, W12 is given as 1 plus W22, so that is this value, plus W11, and since we take the latest value, it should be this. So it is 1 plus E2 plus A3 divided by 4. So that's how we have programmed. So this is for W11, this is W21, which has W31 plus W11 plus W22. So these are coming up like this. W31 we have already seen, that is W21 for which we have the latest value, and W32 for which we have the previous value here, and W12, W22 has W32 which is yet to be evaluated, so that is F2, W12 which is already evaluated, so it becomes D3, this one here, and W21 which is already evaluated, which is this B3 divided by 4, and finally W32 here is W22 which is evaluated, so we put it as this value, that is E3, and W31 which is already evaluated, so that is C3 by 4. So we have put the formulas here, and then let's just erase all this. So this is what the value is at the end of the first iteration, and we can take this down. We can just click and the solution will evolve. So we can see this is the iteration number, so we can put this as iteration number. This is equal to the first iteration, that is the initial guess. This is the second iteration, so we can write this as 1 plus this. Okay, let me just do it again. 1 plus this one. So second iteration we have these values, third iteration these are changing, and we can see that as we go more and more iterations, it is this particular W11 has gone from 0.25 to 0.406, 497, 543, but it is beginning to stabilize. By the end of the 16th iteration, it has become stable up to the 5th decimal point here, 5th decimal place. Similarly, these also have become stabilized, and we have got a final solution which is up to the accurate up to the 5th decimal place as given by this. So this is how we have generated the solution for the 6 unknowns using the Gauss-Seidel method using an iterative scheme. If you were to change the initial guess, for example, if you make this as 1, I think we should have changed. Yes. So if you change everything to 1, the solution is changing, but the final solution will not change. The final converged solution will not change. I can even make this as 10 here. The solution is not changing. The converged solution will not change if I change my initial guess. So that is one characteristic feature of a convergent iterative method. What will change, of course, is the values as they go through the iterative process, they will change, and the number of iterations which are needed to get to the converged solution may change, but the final solution itself will not necessarily change. So this, in this way, we can get a solution to the overall scheme. So this is in essence the CFD approach. What we have illustrated here is for the very simple case with just 6 points, and 6 points will not give us a very good solution. We have to do it for much larger number of points. For that we have to do much more work, but it will be done, and we are going to show the final solution that we get when we increase the number of grid points from what we have here. Here we have 4 divisions in this direction and 3 divisions in this direction. We can make it bigger like this. There are more number of grid points in this direction, more number of grid points, and obviously even these values become unknown. So now the unknowns are as many as this, and we can make it even more by putting further subdividing in this way and in this way. So the more the number of grid points, the more accurate will be the solution, and we will see how the solution changes when we put when we subdivide it further and further. At some point we will notice that with further subdivision the solution will not change, and that is the point at which we have a grid independent solution, and that is the ultimate solution to the governing equation that we have started out with. We have seen that doing it by hand is very tedious. Now we come to the computer, and then we can, once we have a computer, we can easily program this and get a solution for large number of grids. And here we have a table which summarizes the solution for different grid sizes. When you have a 6 by 6, 7 by 7, 10 by 10, 50 by 50, 100 by 100, like this. And we can see that as the grid size increases, the matrix size also increases. For example, if we have 41 points by 41 points, then we have matrix size of 1600 by 1600. We have close to 1600 variables in this, and in each case we can use the Gauss-Seidel method and then get a converged solution. And once we have the converged solution, we can find out the average velocity by taking an average of all the values, and that average value is what is put here in this column. And we can see that for a 6 by 6 grid size we have an average velocity of 0.7409. This is the average speed, and as the grid size increases to 10 by 10 it has come down to 0.6722. For 25 by 25 25 it has come down to 0.6070, and as the grid size increases it seems to be stabilizing. For example, at 51 by 51 it is 0.5843, at 79 by 71 0.5765. So the change is becoming less and less, and 94 by 94 is 0.5742. So it is about 0.57 is the velocity that we are getting as the average velocity, and this is what we expect as average velocity, and the same thing is plotted here. It is the mean velocity that is computed versus the grid size, and we can see that for small grid sizes there is a rapid change here, but eventually it is coming down to about 0.57. And what is plotted in these three figures are the contours of the velocity within the cross section. We can see that for a grid size of 15 by 15 we have high velocity at the center, and otherwise we have almost like an elliptic type of things showing different velocity levels, and at the corners, at the four corners we have low velocity. As you increase the size here it is stabilizing to a particular pattern of the velocity. So, and here you can see some rough edges, whereas here with the increased number of grid points we have smooth contour lines, which is again an indication that we are reaching a stable solution. Stable solution in the sense a converged solution, which is a grid, which is known as a grid independent solution. So this illustrates the power of computational fluid dynamics, that we can now get a velocity variation within the cross section by having large number of grid points spread throughout, and we can use fairly simple methods which are very easy to program on the computer and which are therefore easy to solve, and then get the velocity distribution for this fairly complicated shape under steady conditions. So the methods that we have employed in this are I would say elementary, and which requires only elementary knowledge of mathematics. It does not require much more than this. So there lies the appeal of computational fluid dynamics, that the underlying principles are something that can be understood fairly easily by an engineer with a basic course in fluid mechanics and mathematics. So what we have done in this lecture is to put in practice the CFD method of solution. We have taken the partial differential equation which governs the flow, and we have arrived at a template of an approximate form of the partial differential equation, which is applicable for any grid point within the flow domain. And we have used this template to generate as many number of algebraic equations as there are unknown variables within representing the velocity at the interior points of that particular flow domain. This gave us a matrix AW equal to B. The size of the matrix depends on how many grid points that we take, and we have specifically used one method which is adapted for which is useful for solving large number of these equations, which is the Gauss-Seidel method. And if you apply that, then and if you go through the iterations, preferably and almost invariably on a computer, then we get a converged solution, and the converged solution can be integrated or added up to get the average velocity, to compute the average velocity, and we can find out how the average velocity changes with the increase in grid size, and ultimately get a grid independent average velocity, at which point we can plot the contours like what we have shown here, and this represents the variation of velocity within the interior. So this is how a CFD method would work, but we have deliberately taken a very simple method, and the governing equation is very simple, the geometry of the flow domain is very simple, the discretization method is also very simple, and the solution method is also very simple. CFD can do much more than what is shown in this simple example, and this is what we are going to do in the next several classes. We will introduce complexity in each of these and then come up with a method which can ultimately solve general 3-dimensional flow, which is unsteady, which may be turbulent, which may be reacting, and which may be 3-dimensional. So, in an arbitrarily complex geometry. So, we will try to come up with a solution method which is robust, efficient, and which can also consider the realistic geometries that are present in industrial equipment and realistic flow conditions that are present in industrial equipment. And using these techniques, one should be able to look at a number of scenarios, like what is the optimal distribution of a mixing equipment within a reactor, so as to get highest mixing efficiency at the lowest power consumption in a chemical reaction engineering application. And also in if you are looking at a furnace, boiler furnace, what kind of firing practice must be adopted for a given coal in order to minimize the formation of NOx gases. So, if you are looking at those kind of realistic scenarios, one has to be able to solve 3-dimensional unsteady reacting turbulent flows. The principles that we have enunciated here in this will be extended to deal with those kind of complexities in the coming lectures. So, in the next lecture we are going to start with an outline of the overall course, having now known what CFD is, and then we will go into the each of the modules which represents complications and on each of these things.